Welcome to SanfordFlipMath. This is just us doing some practice problems from 3.6 from the same calculus book that we normally work from. And so this is just a recording from class. If questions come up, I'll just try and restate the question into the mic so people know what's going on. We are just working from problems from the book. So again, this is from our calculus book, which is Finney, Demana, Waits, Kennedy, for copyright purposes, so you know I'm not stealing information. All right, so we're going to do the derivative. They specified a u. Okay, so they're telling us the inside. Okay, so since they're telling us the inside, they're saying that we're already going to treat that like a separate thing. Okay, all right, so in the problems farther down, they don't tell us the inside. All they do is give us the problem, that whole thing, and then we just have to know that this stuff was on the inside. Okay. All right, so the idea here is as we do the derivative, dy dx, we're going to treat this. Now, I could write this with the whole u thing and then the du dx, but I think most people I think that could be helpful to some, but I think most people later on it's not. So I'm just going to do this like I would normally do it. So this is a power, so I'm going to do 2 times, I'm doing the power rule. Is that okay so far? And then I'm just going to I keep the same inside. This inside stays the same. And the only difference is now I have to multiply this by the derivative of the inside. All right, so the question was, the implication yesterday when we were working on this in class was there needed to be a quotient rule. And we haven't done a quotient rule yet. But we also haven't done the derivative of a quotient yet. So this really started out as a power, right? This whole thing is a power, and then all we're going to do then is when we do the derivative of the inside is a quotient. So that's going to be us doing the quotient rule. So off to the side here, I'm going to do the derivative of the inside. Okay, so again, the whole premise of this overall is dy dx equals dy du, and the u is the inside, times du dx, so times the derivative of the inside. That's the idea. This is the chain rule. That's what this is all based on. So here we are doing du dx. Well, I'm not going to have room to do du dx there. I'm going to do the derivative of sine over 1 plus cosine. Okay, so the quotient rule says that, I'm going to slide down if that's all right. So again, that was nice. U equals sine x over 1 plus cosine. So the derivative of that. Derivative of the inside, and then I'll go back and stick it in there. Denominator times derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. That's the derivative of the inside. You'll be shocked to know, probably not shocked to know, that there's actually a much better way to write that. So I can distribute cosine here. Okay, so this is going to be cosine plus cosine squared. This is minus a negative, so plus sine squared. I'm still working on just the inside. What's all of that? So this is cosine x plus 1, since cosine squared plus sine squared is 1. We remember that from back in the dark ages, that scary time during pre-calc when we did identity stuff. Now what I think is super cool about this is, look at this. So the derivative of the inside is really, I don't really want that to be cosine there, I want 1. 1 plus cosine, 1 over 1 plus cosine. This is the derivative of the inside. I had a 1 plus cosine on the top, I had a 1 plus cosine on the bottom, times 1 plus cosine. I can divide one of those factors out. So on the inside, okay, that's the derivative of the inside. So again, power rule, multiplied by 2 here, subtracted 1 from my exponent there, and then I'm multiplying by the derivative of the inside. This is the final answer. Now, the book might I'm going to guess that the book put the 2 on the top and probably wrote 1 plus cosine times 1 plus cosine as 1 plus cosine quantity squared. I'm fine with this. I'm loving it in every way. So whichever is your favorite, that one or that one, Happy New Year, I'm good. Okay. All right, so this is number 11, again from 3.6, and what we're supposed to be doing here is finding derivative, I assume. It says an object moves along the x-axis, so its position at any time is given by this equation. Find the velocity of the object, okay, for t. Okay, so again, velocity equals ds dt, or if it, if it's y, it's dy dt, whatever. It's derivative with respect to time. So we're just doing derivative. Okay, so as I go through here, s prime is ds dt. As we go through here, I'm just going to do the same thing I would do when I'm doing derivative. Now, this is just a big, ugly number. That's all that is. So it's coming along. If I have a coefficient multiplying, it just multiplies. I don't need to do a product rule when I have a constant multiplying or a coefficient multiplying. I can just multiply. Okay? So, and then I need to think, this is sine. Well, the outside function is sine. Where's the inside function? What's the inside function? The 3t is an inside function. This is still like an f of g of x or an f of u or something like that. Okay, so derivative of sine, cosine, of the same thing that we had there. Okay, so the inside is still the inside. What's different? Multiplied by the derivative of the inside, so the derivative of the inside is 3. Okay, so this first term, the whole 4 over 3 pi sine 3t, that part is done. Okay, now I can switch to the other term. Okay, same idea. Okay, so 4 over 5 pi, it's just a constant multiplier, it's a coefficient. Derivative of cosine, I'm going to put parentheses here because I don't want it to look like subtraction. Okay. So this is, because this is negative sine, keep the same inside, those parentheses aren't necessary per se, times the derivative of the inside. Now again, for the purposes of a free response question, you don't have to simplify it, you can be done. Now I think you should be able to simplify it, it's not that big of a deal to simplify this. Remember, this is, you can't do anything with this 3t, it's on the inside of cosine. But this 3 and this 3 can divide out. So this is 4 over pi cosine 3t. Right? This 3 divided out with that 3. Now this is going to be a minus now because it's a negative. And again, 5 divides out with 5. I can't touch that 5 though. Okay, because it's inside sine. Okay, so 4 over pi sine of 5t. This is ds dt. All right, moving along. Again, we're in the chain rule. We are doing examples from yesterday's homework from the Finney, Demana, Waits, Kennedy calculus book. All right, again, we are finding s prime, also known as ds dt, velocity. Okay. Derivative of cosine? Negative sine. Keep the inside the same. We're not doing the derivative of the inside yet. Now we're going to multiply by the derivative of the inside. Well, the derivative of pi over 2 is nothing. Derivative of a minus 3t or a negative 3t? Negative 3. So we could simplify this a little bit. Again, you can be done here. If this is a multiple choice question, though, that's not going to be one of the choices. Right? If you're trying to check in the back of the book, this is not going to be the answer. But negative 3 times negative, so this is going to be 3. That was a good one. I like that one. Pretty straightforward. Okay, so that's just a fairly basic normal change. All right, just a clarification on 9, and I think it was the one we did before this, 11. Both of these questions ask for velocity. But also note that they don't give us a t-value to find that velocity. All they basically say is find the velocity as a function of t. So velocity is derivative of position. So that is the derivative of position. We're done. That is derivative of position. That's velocity. So that's velocity. That's velocity. All right, 17 is asking us to find the derivative, and then it says if you're unsure of your answer, use a numeric derivative to support your computation. All right, so we'll do that for one of these. So 17 works. Okay, so y prime. The big issue here is, okay, we do have a chain rule thing. Like this is really, sorry, this is not y cubed yet. Surprise. There we go. This is not y cubed yet. I'm sorry, this is not y prime yet. Sine of x cubed times tangent 4x. Remember that sine cubed means sine of x cubed. It really means do the sine first and then cube it. Okay, not to be confused with cubit, a unit of measure from Noah's time. All right, so the other thing that you need to see here is how is this thing connected to this other thing? That's a product. That's multiplication. So shockingly enough, if it's a product, I'm going to use the product rule. Okay, so this is u, this is v. So y prime is going to be v times u prime plus u. Oh, I don't really want to write it like that, do I? Sorry. All right, v times u prime, that's going to be a bunch of stuff, plus u times v prime. Okay, so the question then is, what's u prime? And this is, again, back to chain rule now, because this is a sine of x inside a cube. So I'm doing a power rule. Keep the inside the same, raised to the second power, times the derivative of the inside. Derivative of sine is cosine. Okay, so I'm done with u prime. Okay, yeah. No. I have to do 3 times the original inside to whatever power times, and then the derivative of the inside. So you're always doing the derivative of the outside with the original inside, and then times the derivative of the inside. Okay, so again, the idea is when we're doing the derivative of whatever it is, it's going to be the derivative of the outside with the original inside. I will try. I will try to circle the outside in light green or something. All right, and then times the derivative of the inside. Okay, so in this case, this is that outside function. It's something cubed. Right? I have sine of x cubed. I have something cubed. Well, if I do the derivative of something cubed, it's going to be 3 times something to the second. And that something has to be the same something. Now, if that something happens to be a function of x inside of a function, then I'm going to have that something prime, right? That derivative. Okay. I can leave it like that for that part of it, yes. Yeah, yeah. So yeah, d dx of whatever it is I'm taking the derivative. Okay. All right, so I need to do the v prime. V prime, same idea. Okay, now this time the outside is just tangent. So derivative of tangent is secant squared of the same inside, now times the derivative of the inside, 4. So again, I can be done. This is the derivative. Right now, just as it is, I have taken the derivative. It's just an issue of, it's a mess. You know it's not going to look like in the that in the back of the book. Ugh. All right, so that was y prime. So the question is now, can we clean that up? Yeah, we could clean it up a little bit. 3 times sine squared times cos. This is going to look pretty much the same. I'd probably just put the 3 out in front. That's probably the only thing that I would do to change that. And I'd probably the only thing I would do to change this is put the 4 out in front. Unless I saw something where I could combine like terms or something, there's really no reason to make anything really different about that. Okay, so now the question is, this is going to be a lot of fun. Now the question is, how would numeric derivative help us confirm that this is correct? Numeric derivative is when you go on your calculator, kind of like this was, and I do the derivative. The calculator can't do a symbolic derivative. Your calculator can't do the derivative of x squared and call it 2x. But it can do the derivative of x squared at a point and give you a numeric approximation. It's not going to be perfect, but it's decent. Okay, and what's cool about it is, and that's how I showed that the derivative of sine is cosine. I just kind of did a graph of the derivative of sine and a graph of cosine and showed that they were the same. Well, I can do the same kind of thing here. I can actually type in the original function, and this was 17, so this is sine cubed times tangent of 4x. Okay, well, this is going to be great. Yeah, and by great I mean not great. All right, so sine cubed again means sine of x cubed. I don't even really want this here. I want the derivative of this. Sorry. I'll fix it in a second. Times tangent of 4x. Not x. 4x. Okay, so that's the original function I had, and really what I want here is the derivative of this, and I don't know if I can squeeze this in or not. We'll try. Okay, so the numeric derivative is located under math, and it's choice 8. And I'll see it didn't do at all what I wanted. I'm going to have to retype it. It's all good. Okay, so I'm doing the derivative. Now this is on the new system, and I know not everybody has a new system, and I'm sorry. It works on the old system also. It's just you have to know the key sequence. On the old system, it looks like this, and you have to type in whatever your function is with respect to x, and you'd have to tell it at what x value. So for us, what we'd be doing is type in the function x, and if we want to do a graph, we would have x again, because we're saying do that at every single x value. Okay, so let me just, I don't know, maybe that'll stay there. We'll see. All right, so again, what was I doing? Sine cubed. I have to retype it in. Sorry. And then I'll delete it in a second. Delete the other one in a second. Times tangent of 4x, I believe it was. Okay, and then this, I'm going to do this at every x value. If I wanted to know the slope at 3, I would have put 3 here. Okay, and then I just need to delete all the rest of this. I'm going to get frustrated in a second if this doesn't let me delete everything. I'm almost there. Let me get rid of that last little 3. All right, I think I'm there. Woo! All right. This is ugly. Okay, so why is it taking so long to graph? It's working. Yeah, I don't know. That's just something about the way the thing records. Yeah, this is doing, at every single pixel value, this is calculating a slope just a smidge to the left and a smidge to the right. So it's doing little slopes. It's doing y2 minus y1 over x2 minus x1 at every pixel for that complicated equation, and so it's taken a long time. Okay, so what I want to do then is see if now this is doing the numeric derivative of the original function for number 17. Okay, now what I want to do is see, does my answer give the same graph? Well, this is going to be a lot of fun to type in also. Okay, so I'm going to make a quick note here so I know what I'm going to be typing. All right, so for those of you watching along at home, Mr. Sanford's writing on the sideboard so he can type down whatever is going on. I probably should have just paused it. Okay, for those of us watching at home, I took the liberty of typing in. Everything that's on the for my answer from derivative. Sorry, these awkward pauses are me waiting for the class to be quiet. All right, I took some time and typed in the derivative. Okay, so I'm just going to kind of scroll across so you can see how it looks, and again, pause, type as you need. But this is what we got for derivative back on the original problem, and this is kind of an ugly mess to type into the calculator, and it just is what it is. All right, I'm going to hit graph. It's going to take a minute. The calculator's still catching up to my arrowing. There we go. I'm hitting graph. Come on, you can graph. Or not. I guess so. Oh, here it goes. All right. So it's graphing. This is graphing the numeric derivative of number 17. This is what the calculator thinks the derivative is by doing a quick little slope calculation at every point. That's what it's doing. Okay, so then when this gets done, it's going to start graphing derivative, what my answer for derivative was from this whole thing. Okay, you just be patient while this is graphing because the calculator is doing a lot of work here. Okay, the next version will go much more quickly. I have the second one graphing in a thicker graph so that you can tell the distinction, you can distinguish between the two, okay? And here it comes. And so the question is, does it look like the same thing? This isn't proof that it is, but it's really good evidence that says, you know what, I think my derivative answer is right. That's really all this is for. So, you know, when the directions say, if you're unsure of your answer, use numeric derivative to support your computation, it's just saying do n-deriv, or, you know, do the numeric derivative in the calculator, have it graph that derivative, and then match it up to what you think the derivative is. It's easy for you to say. And if they match, then Happy New Year. Okay, so that was the point of that. Okay. I'm not doing that again. All right. Next up. All right, so this is from the next assignment. This is number 29. And the first question is, why is this even in this section? I mean, this is supposed to be about chain rule, and the derivative of tangent it's not a chain rule. It's not a function inside of a function. So if I do derivative, what's the derivative of tangent? Okay, but are we done? Yeah, this question is really asking for y double prime, which is the second derivative. It's the derivative of the derivative. Now, I'm going to rewrite the derivative because, and my only reason for doing this is I just think it's easier to understand what it's doing by doing this. I think it's easier to see it. They mean the same thing. If your brain looks at that and says, yep, I know secant's on the inside, you don't have to rewrite it the way I am. I just think it's easier to follow. Okay? So y double prime then, I have to do the power rule. So that it's going to be 2 times something to the 1 now. That something is still secant of x. And now I'm going to multiply by the derivative of the inside. So this is the inside. And derivative of secant is secant tangent. Now the only thing that, this is done. If you are thrilled with that, then so am I. Some of you I know would say, you know what, that's secant to the 1 is just secant times secant, so you could combine this a little bit. I'm having issues writing sine when I mean secant. Starts with an S. Just because it starts with an S doesn't mean it has to be sine. Okay, and that's it. That's done. Yeah, and green on green was a bad choice. Sorry. All right, those of you watching on the video, if you don't have the book in front of you, page 155, number 62, it will be in a big disadvantage in terms of looking at the graph. I did not, normally when I put something from the book in, I actually just take a picture of it with my phone and then send it to myself, and then I insert it in. So when you see like the rules that I just are stolen straight out of the book, that's what I do. And obviously we're doing this in class right now, so I don't have that here unless I take 5 minutes of your valuable time for me to do that, and that just seems kind of silly. Yeah, especially when we're out of here in like 2 minutes. All right, so in terms of eyeballing the graph, I can't show both things at the same time. Well, I guess I can do this. It's not going to record that. Sorry. But it'll record my audio. In terms of increasing the fastest, aren't we just looking at where the slope is the steepest? So picturing that, I see it looks like it's, somewhere around here. I want to say, bless you, I want to say, yeah, and that will be on the tape, by the way, or the recording. It's somewhere in April, it looks like. And all I'm doing is eyeballing the graph right now. Okay, now, and in terms of how many degrees per day, then that would be somewhere in, I don't know, you can eyeball the slope and look at change in y over change in x, or change in temperature over change in time. Now, the only other issue is, okay, I'm going to, for those of you who are in the room, I'm popping back to the computer so that we can do this a little bit here. Come on. Come on. There it is. All right. Think about where was that steepest? In terms of on the graph, okay, so this is just a speedy little sketch. Wasn't that somewhere in here? Isn't that kind of on the midline? So it's kind of when it's on its way up, and think about how sine normally looks. Normally starts at 0, 0. Isn't that corresponding point that matches there? How far did that slide? How far did that shift? It went to the right 101 and up 25. I'm willing to bet some money that this actually happens at an x value or t value of 101. And this is in days, right? Okay. Now, so the question then is, how could you, what does this have to do with this section? Well, if you take the time, and we don't have it right now, to do the derivative of this. Now, this is going to be a bit of a hoopla, because we got a function inside of a function inside of a, yeah. But it's going to be about cosine, isn't it? And then there's going to be this inside. And then the question is going to be where, cosine is at a maximum normally when we're doing the cosine of 0. Well, to make the inside of this 0, it would be when x is 101. That's really all the time I have to talk about this right now. In terms of finding the rate, the actual rate of change, do the derivative, plug in 101. Okay? All right, well, that was fun. All right, everybody bailed on me, but we're going to go ahead and continue on and do the derivative of this thing. And I know this recording is going long, but again, it's not assigned. All right, so if we're going to find where the velocity is max, sorry, rate of change is max. It's technically not a velocity. And we actually want to find that value. We're making a judgment call that it probably has something to do with x minus 101, so probably at x equals 101. But we still need to find that actual velocity. So in order to do that, or that actual rate of change, so in order to do that, we're going to do the derivative. All right, so the 37 is just coming along. So, and then the derivative of sine is cosine. And then we keep the inside. This is a function inside of a function. Okay, so this is where the chain rule comes in. Okay, we're keeping the inside the same. I'm going to get rid of this foo-foo stuff over here. We'll revisit that as we need to. Okay, and I'm still doing the derivative of sine because now I have to do the derivative of the inside. Well, the derivative of the inside of this thing is just going to be, well, the 2 pi over 365 is going to come along. 2 pi over 365 times, and now really I'm just going to think of this kind of like it's in its distributed form because I think that's just easier. Yes, that will be on the video. Get rid of that, get rid of that. Okay, cool. So 2 pi over 365x is just, the derivative of that's going to be 2 pi over 365. The derivative of 2 pi over 365 times a minus 101, that's just a constant. That's basically done. So there is no x to go with this. I can get rid of that. And then the last thing to consider is the derivative of 25 is 0. Okay? So that is derivative, yeah.
Okay, so I did that.
All right, so continuing on. If I want to know the maximum, well, a maximum for cosine, again, and I think we said something about this just a second ago, but cosine normally starts at the top at 0, and then the next one would be whatever the period is. So that's the normal flow of cosine. Well, what makes, and again, so that would be at x equals 0. Well, what makes the inside of this thing 0 is an x value of 101. Okay, so if I want to know what that maximum rate of change is, then really I'm just going to put 101 into the derivative. So this is now, so this is going to be kind of exciting, and by exciting I mean like, really, is that it? 101 minus 101 is 0. 0 times 2 pi over 365 is still 0. The cosine of 0 is 1. So really, this whole thing in the middle here is really just 0. Okay, so if that's true, then really all I'm left, I'm sorry, is 1. I lied. This whole thing in the middle is 1 because yeah, I can't see that at all. Because the cosine of 0 is 1. Okay, sorry, I spoke too soon. All right, so ultimately this just becomes 37 times 1 times 2 pi over 365, and so I guess that'd be 74 pi over 365, and I think this was in degrees Fahrenheit, and this is per day, I believe, where x is the equation approximates on day x, yes, per day. That is the maximum rate of change. Now, what a beautiful number that is. Now, I'm going to say that, so 74 times 3 would be 210, 21, so about 200 something over 365. Yeah, it looks like the book, I'm on track with the book's answer, which is 0.637 degrees Fahrenheit per day. Okay, that's it.